This is Albert Einstein. When he was 16, an idea came into his head. He thought that the previous thinking of speed and time being separate was wrong. Einstein wanted a theory that was more consistent with speed and vantage point. The experiment that he ran in his head was if a train was moving on a track near light speed and lightning struck two trees on either side of the train, he would see the one that he's moving toward first, and the one behind him he would see later. But a person standing still in the middle of both of those trees would see them at the same time. Similarly, if you had a person standing on Earth and a person on the International Space Station, time would affect both of them differently because they're moving at different speeds.
So energy is what makes an object and time dilate. So to figure this out, he used E equals mc squared. So we're going to use E equals mc squared to figure out how much energy is going to be in one paperclip. So one paperclip is equal to 0.001 kilograms. So 0.001 kilograms times 3 times 10 to the 8th squared is 0.001 times 3 times 10 to the 16th. And that'll equal about 3 times 10 to the 13th, which is going to be roughly around 7.1 kilotons of TNT. That is about like 4 times more than the atomic bomb on Hiroshima. Similarly, we can use the same equation to figure out how much energy is in about one person. And for one person, we'll just use one Josh. One Josh is going to equal about 190 pounds. 190 pounds times 0.45 kilograms will lead you to the actual kilograms unit of one Josh, which is 85.5 kilograms. And using our equation equals mc squared, we plug in 85.5 kilograms times 3 times 10 to the 8th squared, and that'll be 85.5 times 3 times the 16th will equal around 226 times 10 to the 18th joules, which is going to be roughly around 621,414 kilotons of TNT.
After special relativity, Einstein came up with general relativity, which explained the fabric of space-time. So here, we have space-time with no mass, a small mass, which creates a small divot in space-time, and then a large mass, which creates a bigger divot. If you look at space-time from a top-down point of view with the mass, you can see that the mass creates gravitational waves that move throughout space. These waves move at the speed of light.
So now, if the sun were to disappear, how long would you think it would take us to notice? The answer to the previous question would be roughly around 8 minutes. This is because gravity has to travel at the speed of light, because non-mass particles has to travel at a universal speed limit, which is the speed of light.